We're going to take a look at practice question set number 27 here now, starting with question number 1. It says experiments with cathode ray tubes led to the discovery of the, we should be able to nail this one, right? Two electrons, yeah. Remember that Thomson, when he did his experiment, he measured the charge to mass ratio of the electron, he found, or of the cathode ray, and he found that it was 1.76 times 10 to the 11. That number that we have right there, you don't need to remember that number, but you do need to know that that number is really, really big, yeah. In fact, so big that the mass must be really, really small. If the charge to mass ratio is bigger than the charge to mass ratio of the smallest atom, then the mass must be smaller than the mass of the smallest atom, hence subatomic particle, hence it's an electron. He had already established that it was a negatively charged particle by the way it was deflected in a magnetic field. Now we know that it's a subatomic negatively charged particle. 2, the property of cathode rays that provides the best evidence to suggest that they are not EMR is that they, what? I don't like the word best. Whenever I see this, it kind of scares me because it makes me start thinking like, oh man, there's going to be like 4 answers that are all pretty good, but one of them is better. And this one works pretty good, actually. I wouldn't worry so much about that in this question. What is it that provides the best evidence to suggest that these cathode rays are not EMR? How did Thomson realize that they were charged particles? Not subatomic charged particles, but just charged particles. Remember that last chamber, that main chamber of the cathode ray tube? He found that those charged particles, or those cathode rays, ended up going in a circle, right? And it was because of a magnetic field. Charged particles can be deflected in a magnetic field, but EMR cannot be deflected in a magnetic field. So that's what told them that they were negatively charged particles, and then it was the charge to mass ratio that told them that they were subatomic negatively charged particles. 3, an experiment is designed to study the charge to mass ratio of hydrogen ions. This isn't a cathode ray tube because we're dealing with ions here, right? But same thing. We call it a mass spectrometer. Works the same way. Same 3 chambers. We want to find the equation that describes the radius of curvature of an ion's path. What section of the mass spectrometer would this be if you're looking for the radius, the circle nature of it? Yeah, it's the main chamber is the only one where the particles go in a circle, so that's what it's got to be. We set 2 forces equal to each other in the main chamber. What 2 forces are those? We've dealt with 3 of them so far in this unit: the electric force, the magnetic force, and the force of gravity, and the centripetal force, I guess. Which 2 forces do we set equal to here? Nick? Fc and Fm. Good, Fc and Fm. Fc is mv squared over r, Fm is qvb. One of the v's cancels on both sides. We're left with mv over r equals q times b. Now we want to rearrange this to solve for r. Not too big of a deal here. Take the r up by multiplying. We get mv is equal to qbr. And then we take the qb over to the other side by, Anna? Dividing, right. So r is equal to mv over qb. And the answer for this one is going to end up being, what is it? B. Now, we're going to use this, this equation. We're going to use this equation in the next couple of questions as well. We're not going to derive it again. But if the next question, say, was a standalone question, we could derive it in exactly the same way as we just did derive it. The next question, question number 4, says, a graph that shows the relationship between radius and the strength of the magnetic field is? Well, whenever you want to find a relationship, whether it's graphical or otherwise, we're going to say R is equal to mv over q times b. Now, which graph is going to show us the relationship between R and B here? As B goes up, what happens to the value of R? As B increases, R, Cameron, goes down. Good. So that means the answer is not going to be A or B, because you can see in both A and B, as the magnetic field goes up, R goes up. It's a different relationship. Neither one of them are linear, but as B goes up, R goes up in both of those cases. So it's either going to be C or D. Which one is it? It is D. Yeah, it is D. You're not going to see a graph in physics 30 that is shaped like C. D we see fairly often. This is y is related to 1 over x, Or it could be y is related to 1 over x squared. Could be either one. They both look almost the same. But you're not going to see one that has the relationship of C. The answer is definitely D here. All right, now I got a follow-up question to this, and it kind of gets addressed in the next question, but I want to touch on it here. If I have this graph, R versus B, and I want to analyze this, I want to deal with this, I can't. I can't deal with this in the form that it's in. I have to have a straight line to analyze. So how am I going to straighten this? What graph would I have to plot in order to make this a straight line? Good, 1 over B. R versus 1 over B. We know that it's 1 over B because the equation is R is equal to something over B. So if you plot that, then that gives you a straight line, and then you could deal with it using y equals mx plus b, right? Because it's a straight line. Now the next question kind of goes to that. It tells me what graph I had to plot in order to get a straight line. So the slope is related to the charge to mass ratio. We want to know the expression that gives the correct value for the charge to mass ratio. In other words, we want to derive the meaning of the slope and then relate it to the charge to mass ratio. You guys remember how to do this, right? We've done this 6 or 7 times on labs now. The equation for this line is what? What has it been? Good. Y is equal to mx plus b. Good. And on the y-axis is what variable, Taylor? Good. M stands for Parker. Slope. Good. X is, Nicole, what's on the x-axis? Good. This little b here is the y-intercept. Is there a y-intercept here? Is there a y-intercept? No. No, there isn't. There's no numbers here, but we can pretty clearly tell it goes to the origin there, so we can cross that off. Okay, next equation comes from our data sheet. Maybe we have to derive it. Turns out it's going to be R is equal to mv over qb. It's that one we derived a couple questions ago. Let's cross off R, because it appears in both. Cross off B, because it appears in both. We're left with slope over here is equal to mv over q. Right? But remember, we wanted to solve for the charge to mass ratio. I don't see q over m there. I see close. I see m over q. Just rearrange it, that's all. Rearrange it to solve for q over m. The q goes up. I get the slope times q equals m times v. And then take the m down and the slope down. And I end up getting q over m is equal to v over the slope. So the answer to this question, charge to mass ratio, is represented by the expression, what was it? Forget already. So that was when you're old. V over the slope. The speed divided by the slope. The answer would be C for that one. Is that good? 6, to determine the speed of the charged particles in a cathode tube, Thomson balanced the forces produced by, what section of the cathode tube would that be? Speed of particles, balancing forces, that would be the middle section. The velocity selection chamber, which two forces, Matteo, did he balance? One's positive, one's negative, but what are the forces? Gravity? Tim, help me out. No. The electric and magnetic. Remember Fe. Yeah, you did. Yeah. Yeah. It's kind of like saying it's a multiple choice question, and you have 4 options, A, B, C, D, and I ask you what the answer is, and you say A, no B, no C, no D. You can legitimately say that you actually gave me the correct answer at one point. Yeah. Yeah. Fe is equal to Fm. Remember, if you introduce Fg, that's normally in the oil drop experiment. Fg isn't significant in the cathode tube because you're dealing with the force of gravity on an electron, and it's just too small. In the oil drop experiment, it's much bigger because you're dealing with the mass of a oil drop now. So no gravity. There's gravity in the cathode tube, but we ignore gravity because it's so small. 7. Alpha particle moves without deflection. Electric field, magnetic field, what's the speed? That's the velocity selection chamber. Fe equals Fm again. Say QE equals QVB. Cancel Q. V is equal to E over B. We don't know what E is, but we can find it. What's the equation that we use to find the value of the electric field between two plates? Delta V over delta D, yeah. Delta V over delta D. Make sure that you convert this to meters. That's going to be 0.04 meters. Do your thing here. Divide that by B, and we end up getting D 3.41 times 10 to the 5 meters per second.